Hello, my name is Matthew Kwan, and today I'm going to show you how to do the bright fringe dark fringe problem on problem set 5 for physics. Now, the problem tells us that given a light of wavelength with a wavelength of 413 nanometers, and given that it gives a fourth order bright fringe at a certain location on a flat screen, what is the longest wavelength of visible light that would produce a dark fringe at the same location? And for this problem, we are going to assume that the range of visible wavelengths extends from 380 to 750 nanometers, so our result should be within that range. Now, right off the bat, we have to write down our known values. You can see that I've already written one down, delta L, which well, there's multiple ways to describe this, but the way I've described it here is the difference between light paths from each slit to the screen. Now, other information it gives us is that the wavelength of the light is 413 nanometers. It also tells us that it is fourth order. It gives a fourth order bright fringe. So, for the bright fringe, m equals 4. And what it wants us to find is the longest wavelength of visible light that would produce a dark fringe at the same location. Now, it should also help us to write down the range. We want to make sure that our final answer is within that range. So, this would be our range. Now, this is not 380 minus 750. This is a range of 380 to 750. Our final answer should be between these values. Now, the first thing we should do is that we should recognize that in order to use the information we have, we can better draw a diagram, a basic one to save time, so that we can better visualize this problem and associate it with a formula. Now, this is for Dr. Young's double slit experiment, so you can draw 3 lines to represent the 2 slits, and then the problem tells us that it's for a flat screen. Now, if you can visualize each of these segments as an order, and I'll just draw these arbitrarily to make them, just to simplify things. And we know that we want the bright fringe to be at the same location as the dark fringe. And to do this, we need to set up an inequality. But we can't set up an equality right away. Otherwise we'll introduce too many unknowns. So right off the bat, we can't just set up a system of equations. That's jumping a little bit ahead of ourselves. The first thing what we really want to do is to associate with a formula that will essentially get us to step 1 of the process. Now, one formula that immediately comes to mind should be a formula that uses delta L, as well as the other given values, in this case being the order and the wavelength. And we can extend this, for the purposes of this problem, to also equal this, because what this represents here, m plus 1/2, is essentially just we're going to be for this problem we'll be starting with an m equals 0, and we're basically going to be reiterating that with each time adding 1 to the m until we get a wavelength that is within our range. Now, if that sounded a bit convoluted, you'll see what I mean in a second. Now, I did mention earlier that what we want to do is to set up an equality, because we want our dark fringe to be the same location as the bright fringe. But we also want it to be the longest wavelength possible while still within this range. So now that we have our formula, we can insert our values, and for our initial calculation, we can use the simpler form of the formula I've written down, that being delta L equals m times lambda. In this case, we'll use our given values right off the bat, and that should give us 1652 nanometers for our delta L. Now this obviously is not our answer. For one, it's beyond our range. What we really use this answer for is we're going to use it to set up an equality. Because these terms are all equal to each other, we can use our calculated result from this calculation, and using this formula here, we can set up an equality like this. And what we want to find is the lambda. We have our delta L. In this case, this would be our desired location. And given a certain order, we want our lambda to equal this same location. And the easiest way to do this, the most straightforward, would be simply to have m start at 0, and then add 1 to m, then add 2 to m, and gradually work our way up until our answer meets the requirements of the problem, in this case being that it fits within the range and that it is the longest wavelength possible within that range. Now, you may think that this could mean a lot of calculations, but you'll see that once we start doing the math, it really doesn't take that many steps until we get what we want. So to start off, for our first iteration, we'll have m equals 0, and then I'll add 1/2 to that. And from this equation, from here, this is basically just a calculator work. And in this case, lambda would equal 3304 nanometers. Does this fit within our range? Well, think what you will, but I don't think it does. Okay, time to move on to our next calculation. This time we're going to be using m equals 1, and we'll do this calculation again. And I bet you can see now where this is going. We essentially do this again and again until we get what we want. And in this case, lambda would equal 1101 nanometers. Does this fit within the range? Nope, it does not. So we'll go one step further. And before you tell me that this is getting quite repetitive and frankly pointless to display, allow me to tell you that in this case, lambda yields approximately 661 nanometers. Does this fit within our range? It does. And if you continue forward, you'll know that the future values will not actually fit within this range. So after only 3 iterations, we know that this is the wavelength that we want. This right here is the longest wavelength of visible light that would produce a dark fringe at the same location, in this case being 1652, as the bright fringe. Now that we solved the problem, we can go ahead and check it. And the easiest way to check it would be simply to, well, I could best describe it as essentially redoing the calculation. You could insert lambda 661 back into here, and that should yield 1652. Just to better clarify, this here should give you 1652. Now, just to do some non-calculator work, in order for you to better visualize this, you know that 2 plus 1/2 is 2.5. You know that 661 times 2, which could also be this plus 1/2 of 661. Now obviously if you have a calculator you wouldn't have to do this, but sometimes if you do it by hand, it's easier to verify whether your answer is true. Now what is 1/2 of 660, that is approximately 330. And what do you know? It gives us 1652. So, upon checking our work, our answer is correct. Thank you.